All right, just making that clear. That's 20 feet. And so it's asking the optimal tilt for the solar panel is between 58 and 60 to the horizontal. So we're trying to find an angle. And it happens to be this angle right here. So has Keenan placed his solar panel at the optimal angle? How do we find that theta right there, considering that we're only given side lengths? So, what was it?
Law of cosines.
Why are you saying law of cosines? Good. Okay. So first thing, it's not a right triangle. So we're not using trig ratios. This is an angle, so the Pythagorean theorem wouldn't help anyway. So right triangles, that kind of thing. We're given side, 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 or SSS. So we're going to use law of cosines. Good. So start by writing the actual law out. And then which side are we forced to label and which sides don't actually matter? Like which side has to be a certain side in this case?
A.
Yeah, which is what though?
19.
Yeah, good. So the 19 is across from the angle of interest, and so it has to be in the a squared, the little a squared spot. Otherwise, the rest of this we just plug in. So we have 18 squared plus 20 squared minus 2 times 18 times 20 cosine of theta. And this is the solving for angle version, so it's the one you have to be careful with your order of operations. And take it slow. The biggest issue is always going to be with this subtraction symbol right there. Otherwise, most of the rest of it goes pretty well. I think 18 squared is 256, is that right? Yes? 324, I was close. Okay. All right, then what is 19 squared? All right. I guess next step, probably combine these two at the beginning, so 724. And again, here we see that it would be so nice if we could just subtract, right? 724 minus 720 and get rid of these big numbers and just have this little 4. But we're not going to do that. So just reminding you, don't subtract. At least not between the two there. But we can subtract the 724 off both sides. So let's get that off of there. And yesterday I mentioned that the other side, the left side, sometimes is negative, and that's totally fine. Can someone do that for us? 361 minus 724. Thanks. 360. Thank you. All right, and then let's divide the 720, the negative 720. And what do we get there? 0.5, 0.5 something. All right, how do we undo cosine so we get theta by itself? Go ahead, Saphira. Nope, that's not how we say it. Yeah, good. You're right. Inverse cosine of both sides. Now, I'll tell you why we don't say it that way, and it's because if I have x to the negative 1, and it's actually, we're not saying inverse of x, but actually negative 1 power, we say x to the negative 1 in that case. And it means 1 over x. Okay? In other words, put it in the denominator as a positive. So it does actually have two meanings, which is kind of weird. Anyway, those cancel on the right, and that leaves us with just theta, and then the inverse cosine of 0.5 should be roughly 60 degrees-ish. 59.7. So did he get it in the right range? Yeah. Remember the question, did Keenan place his solar panel at the optimal angle? And he did. Yes, he did. How'd you do? How'd you do? Okay. All right. If you ever decide to put a solar panel, maybe you'll be doing this as well. Think so? Why? That's like a trend right now. A lot of people are paying money for solar panels, so you don't think you'll do it? Oh, brother. Okay. Let's check the homework. You could put it up yourself, I think. Yes.
Answer key on the homework was like all mixed up.
It was?
Yeah.
Okay. That's annoying. What do you mean by like out of order or wrong?
Well, it would say like it was the answer number 14, but it was really the answer number 13.
That's weird. Okay. That is not even the right one. Any of these you'd like to talk through or do, since you did have the answer key, but any you'd like to do? She said it's mixed up though, out of order. Yeah?
14.
Okay. All right, so find f to the nearest whole number. And it doesn't, I like these because this will be more like what you see on your test on Thursday, which is to say it doesn't tell you what to use. So you need to get really good at walking through the questions. First question is going to be what? Is it a right triangle? And we know it's not. Actually, we don't know it's not. We just don't know that it is. So we can't use right triangle trig if we don't know that it's a right triangle. Okay, number 2, what's our next question? Well, we're only given 2 sides. Is the angle between those 2 sides?
Yeah.
It's not. Between would have to be f. So it's not side angle side, it's not side side side. So don't use law of cosines. What about this? What's that? What have we called that? Yeah, so we have an angle and its opposite side. Okay. So we're going to say that means what are we going to use? Angle and its opposite side tells you law of sines. Okay. So we'll start with what we know, which is sine of 36 over 62. And then sine of f, maybe. Sorry, we need e first. Sine of e over 71. Now, why do we have to go to e, even though it has nothing to do with f, with little f? Yeah, we only have one angle. And so we can't use law of sines to get little f if we don't know its opposite angle. We can't plug it into the law of sines. So if we can get angle E, then we can subtract to get angle F, big F. Okay, so we take our cross products as usual, and we get 62 sine of E equals 71 sine 36. And then we want to get sine of E by itself, so we'll divide by 62. And we'll get sine of E there. Okay, how do we undo sine? Inverse, so we'll do sine inverse on both sides. And that whole right side goes into our calculator. So E equals, hold on, let me go put it into radians, to degrees rather. Okay, we get 71 sine 36 over. So inverse sine of 71 sine 36 divided by, what's the bottom number? 62, thanks. Okay, so angle E is 42.3 degrees. All right. Now what? Yeah, Zeke. Yeah, so we need this angle so that we can get do the law of sines opposite of little f. So 36, 42.3. .7. Sounds like a radio station. All right, now what? What? Yeah. Yep. Start over. So sine of 36 over 62 again. Keep using the given relationship instead of one that you solved for as much as possible. In this case, we don't really have a choice, but we can keep the left side the same. Okay, then we just solve for f. So do this all over again. And we'll get f sine 36 equals 62 sine 101.7. And we'll just divide by sine of 36. Let me show that, and then I'll just write the answer. This is just reminding you to make sure you're careful with your parentheses. Okay, and we get 103.3. Now, does the triangle look like it should be that? That's why we don't trust pictures, just information. All right, any others? Corbin, you asked about that one. You didn't look up once.
Yeah,
You did?
yeah, I did it.
Good. Good job. 12, okay. Okay. So she's asking about 12. It is law of cosines because we have side, angle, side. And it's not a right triangle. So law of cosines. And let's see, I'm gonna have to write little, I think. Well, first of all, the known angle and the opposite side is not labeled. There we go. So that's the only thing we can solve for right now, is where I put little b. So little b squared equals 15 squared plus 19 squared minus 2 times 15 times 19 cosine 120. Okay. So now we go solve for that. And I think I'm just going to put it all in the calculator, but we do have to square root the whole thing. Help me remember all the pieces. So square root of 15 squared plus, it's 19 squared, right?
Yeah.
Minus 2 times 15 times 19 cosine 120. And so that side length is 29.5. Now, why did that help?
How we can do this log cosine.
Yeah, now we have this angle and opposite side pair, and we have a 15 across from angle C, so we can use law of sines. And our sort of given, we had to calculate the length, but it's sort of given. The known relationship, sine 120 over 29.5. And then we have sine of C over 15. And so we'll just set up that 29 sine C equals 15 sine 120. And divide by 29.5. And take the inverse sine of both sides. Does anybody else's calculator use the arc notation? Okay. All right, so C equals now one thing I could do is go grab this and bring it down there if I wanted it a little bit more accurate. Probably doesn't matter too much in this case. So we get 26.1. And what do you need to label that? Degrees. Did that help? Okay, any others? Okay. So you had the answers to the rest of them, although apparently mixed up. But was it decipherable? Like you could figure it out? Okay. So give me a fist to 5 on law of sines specifically. Just law of sines, fist to 5. Okay. Law of cosines. Okay. It's acceptable. It's not as good because it's just a little bit awkward. Do you agree? Now, I will say, I feel like at this point, solving for a side length with law of cosines should be okay. Because it's just plug in everything and square root it, essentially. The angle one, like we started off with, that was our warm-up. Let me go back to that. Like this, is that the one that's giving you a little bit of a headache? Law of cosines? Do you want to, we need to start talking about in context. And that's our last topic for law of cosines and law of sines. I'll have a couple examples to show you. I mean, we did one here, didn't we? Was that a big deal? I mean, it's here's how I'll ask that. Assuming that you identify the correct idea, it should be okay. Does that feel true? Like the correct strategy, I mean, whether it's right triangles or law of sines, law of cosines, okay? So do you need to do another angle solving with law of cosines before we start? Or we want to just practice it as we do those kind? Huh? Okay. Let's just do some. The one, you remember the Christmas tree one? At least that's what it looks to me like. Now, don't write all the words, please. Just sketch the picture. And I'll zoom it for now, so you can just sketch the picture. All right, let's go ahead and work on it. So, first of all, I wrote here that it's law of sines. How do we know that? It's not super obvious, is it? So this is what you're going to be doing when we go outside and I think we'll just use clinometers on the phone, but I could show you how to make one too. But anyway, this is what you'll do. And I have done this. I'll show you an example of something I use this on. But basically, you can see either position is a starting position. You measure two angles and the distance between the two places that you measure them. It's super fast and it's super easy. So let's say I wanted to do the flagpole. You hold the thing at your eye, of course, and you get an angle of elevation up to the top of whatever object it is. So I just measured an angle, okay, and then you don't have to go very far. However, that was maybe the 8 feet. Okay, and then I measure another angle, and you can see that this angle is less steep or smaller, right? Like if I'm right below something, I have to look pretty high, and the angle is pretty big, like 80 or something. And if I'm farther away, I'm looking lower. We've seen that in our applied problems before. Everybody good on that? Okay, so it's really just those three things. Angle, you could drop a tape measure, we will, so it's accurate. So walk a little ways, do another angle. It literally takes maybe 1 minute to 2 minutes to measure. Way faster than what we did before. Okay? Now this height of the person's eye, we don't even consider that until the very end, and we just add that on. And we've talked about that before. Like if I'm doing my whole triangle from eye level, At the end, I just need to add that extra 5 feet to the total height. So that's an easy step right at the end. Otherwise, it doesn't play a role. Okay, so let's go ahead and put that on here. Add at the end. Otherwise, just ignore it till you get to the very end. And that's only because we're holding our tool at 5 feet off the ground. Okay? If the thing was on the ground, then you wouldn't even worry about it. But that's just not convenient. Especially like this picture shows that we're out in the snow. Okay, so 2 quick measurements of angles and then a length along the ground. You don't have to be by the object like this one shows. There could, if we wanted to, we could say there's a fence right here. We can't even get over the fence to go measure this tree. It doesn't matter. We can do it from on this side of the fence. Okay, maybe we're trying to measure the height of an object across a gorge or something. I don't know. I don't know what you guys like to do, but I explore and hike a lot, so I like to know stuff like that. Okay. So we've measured our 2 angles and the distance between. And this is law of sines because I know that this length is 8 feet. And I can get this angle up here. Let's call it theta. Without actually doing any trig. Anybody know how?
I'm not gonna say this is full information, but since it's a straight line, it's perpendicular, so the 47 right there is a linear, for those two, where that triangle splits, that's a linear pair. So you would,
Okay, so she's talking about right here being a linear pair, which is true. You said perpendicular, I wouldn't say that, but that's a linear pair. Yep, okay. And then we can get the angle inside the triangle and get that 3rd angle. Now, why do we even care about theta? Why do we need that one? It's the, yeah, that is perfectly stated. It is opposite of the only length we know, right? So we have to have that angle to do anything. So theta is opposite of the only side length that we have. Okay, so let's go ahead and find theta. So this angle is 180. I'm going to change colors on that. This is 180 minus 47, which is what? 133. Okay. And then theta is 180 minus 36 minus 133. And it's pretty teeny. And it will be. Like that top angle will almost always be pretty small. Okay, so what is that? 69, so 11, I think. Right? 11 degrees. Everybody good on how we got that? You have to do that too when you go do this for real. Like you measure those 2 and then you find that top angle. All right. So here's kind of the strategy, and then I want us to draw 2 separate triangles. So I'm going to tell you kind of the strategy first, and then we'll go do that. We need one of these 2 lengths. Okay? It doesn't matter which one you pick, but you need one of them. Then once you have that, you're going to use that length and switch over to right triangle trig to find the height of the object. So that saves you a little work. Now you can still do law of sines, but right triangle trig is faster. Okay, if you find the longer length, like the outer length, you would do that right triangle. If you find this inner length, you would do this right triangle. Okay, but either one, I'm tracing over the height of the tree, right? So either one I get to use, I can use either one to do the height. So decide which one you want. It doesn't actually matter much because we know all the angles. And let's go find the height, or the length, of one of those diagonals. So let's catch up on steps. So first step is to find, and this is just this version. I'm not saying they're all like this, but find the upper small angle. With linear pair and triangle sums. Okay, so we just did the linear pair down at the bottom, and at the top we did a triangle sum. All right, step 2. Find the length of one diagonal. Now, out in the reality, do you see those lines? No. It's what you're looking along. So they're not actually there, right? It's an imaginary line, but we still need the length of it. And we're going to use law of sines for that because we have an angle and its opposite side. So in this case, which one do you want to find? It actually doesn't matter. Which one? Do you want the shorter one or the longer one? I would say I usually do the shorter one, and it's because it's using this angle that we measured instead of this angle that we calculated. So I would use the shorter length myself. But you don't have to. Are we good on that? Maybe call it x. So seriously. Sine of 11 over 8. That's our known relationship. The top skinny angle over the side length measured equals sine of 36 over x. Okay, let's go ahead and solve this. So x sine 11 equals 8 sine 36. So x, I'm not going to show that step. Let's just punch it in. 8 sine 36 over sine 11. So it's 24.64. Okay. Any questions on how we got that length? Everybody's good? Okay. Now we're going to switch, like I said a second ago, we're going to switch over and do the right triangle. With so switch to the right triangle for the height. And right triangles are easier. At least they should be. Okay, so this is the right triangle we're talking about. Note that we have an angle and a hypotenuse now, right? Okay, so let's pause there. We'll come back and finish. Yeah. Yeah. Just, you'll have to do the pass. Let me log in. Okay, so we got this diagonal length, and guys, this is all calculating. So remember, we're just making the 2 angle measurements and 1 short distance measurement, and then we just go to paper, and everything else is calculation. Definitely you should draw a picture. So we're switching now to the right triangle, and this will be a consistent pattern. We want h, the height of the tree. We know the hypotenuse, and we have this angle from measuring it. So what relationship relates those 3? Sine, right? So it's going to be, this is just now right triangle trig ratio. So sine of 47 equals h over 24.64. Okay, again, you can do law of sines again if you want. You can just do law of sines, law of sines. And what you'll find if you do law of sines on this triangle is that it boils down to what we just wrote. Because you'll end up with sine of 90 over 24.64. Sine of 90 is just 1. So you end up back here. Same thing. Okay. And to solve for h, we know we just multiply both sides by 24.64. And so h is... Actually, I'm going to grab that number. 24.64 times sine of 47. And we get 18 feet. Are we done? Okay. Why not? Yeah, good. So I guess step 4. Then add the height of your eye. So our overall height is 18 plus 5, which is 23 feet. Does that seem reasonable for a tree to be 23 feet? Yeah. Okay. So if you go cut Christmas trees with your family and you're wondering how tall your tree is so you don't get too tall of one, now you can do that. Yes. Yes. Kenzie, too. Why not? It's like 3 minutes of work. Well, that's because I had to teach you it, but now you should be able to do it in like measure in 2 minutes, calculate in 3 minutes. So 5 minutes, you could be like, that's a 20-foot tree.
I'll take that.
Okay. Now, if your tree's tall enough that you can just use your arm, or like short enough. But if you have if you're trying to get a big tree, right? Any questions on that? Okay, you will have a problem like this on your test. So you need to know how to do this without putting it on your note card. Remember, you can't put the example on your note card. If I quickly summarize, it's this. You have this skinny triangle here that you find one of the 2 diagonals in using law of sine. Then you switch over and find the height using right triangle or law of sines again. And then you just add the distance that you held the tool from. Okay, I'll be honest. This is my last box. I guess most of you don't use this, but for me, here's what I want you to write. Kind of a little flow chart. What's our first question? Okay. I would even before that say, am I solving for lengths or angles? Because can we use Pythagorean theorem for lengths? Sorry, for angles, excuse me. No. Okay, so first question is lengths or angles. Okay, if it's lengths, I'm going to set this up, like I said, like kind of an algorithm, like a flow chart. Okay, then your next question is it a right triangle? If it is, what tools do you have in that case? We could make this super detailed. We could say, okay, yes, it's a right triangle. Is it special? Or is it not? Like, I'm not going to do it that way. I think it gets a little busy. But I'm just going to say at this point, if it is a right triangle, consider special right triangles. Trig. What? Ratios, yep. Okay, if it is not a right triangle, we don't have that many options, right? If it's not a right triangle for lengths, what are we using? Not a right triangle, what are we using? Yep. So I would say angle and its opposite. That would be the next question. If it's yes, then you're doing law of sines. If it's no, now we have to ask what? Can we just say, hey, law of cosines works? Well, now we need to say, is it SSS or SAS? And if that's true, then it's law of cosines. If it's not, don't worry about it. Okay, that branch we're not going to deal with. Okay, if we are solving for angles, what tools do we have for that? Well, our first question is still, is it a right triangle? If it's yes, we only have trig ratios, or not only, but that's what I would recommend. But in fact, let's put inverse trig ratios so we don't forget that. Inverse trig ratio. Okay. If it's not a right triangle, what do we have? Yep. Basically that whole same thing, okay? So if it's not, and then I'm just going to say C left for law of sines or cosines. Okay? In other words, just look over where we already wrote it. It's the same thing. So guys, you're going to have to think through this on this test, right? Each one of these problems you're going to have to ask, like, what am I dealing with? At this point, we have quite a bit that we can use to solve. My suggestion, just like I showed you here, if you're dealing with right triangles, trig ratios. That would be the best option. Otherwise, you're dealing with law of sines or cosines. Okay? So let's run through. This is not going to be solving. This is going to be which one are you going to use. So don't shout it out. I'll give you a second to look and think, and then I'll ask everybody. Again, we're not going to solve these. I'll give you a chance to work on your homework here in just a bit. Okay, there's your picture. You can see part A says what is AB, so this length here. So again, think through that algorithm, that flow chart. Which strategy would you use to solve for AB? Don't shout it out. We'll say here in just a second. By the way, I know this is hard to read. This is 99.4 right there, and 19.8 right there. And we're solving for AB, at least in the first question. By the way, there's that 7.6 up there at the top. Hi.
Hello, can I do lunch
Yep.
tensions? Corbin. Lunch tension.
He went to the nurse.
Nurse? Okay.
Yeah.
Alright, that's it. Thank
Okay.
you.
Yep. Okay. All right, what's your vote? What would you use? I hear law of sines, and I agree. We have an angle and its opposite side, right? And it is not a right triangle. So I would agree with sines. Good. That would get us, we can vertical angle the 99.4 here, and then we could set up sine of 19.8 over 7.6, etc. Good? Everybody see that? Okay. All right, let's go to this one. This is kind of an awkward picture, so you'll need to let your eye, like read it, and then let your eyes kind of look at it to see what the situation is. This is like one of those tall radio towers, tall skinny ones. So again, angle or side length. This is side length. Is it right triangle or not? Etc. Just think through that algorithm. Here's the scenario. Radio tower, cable hooking onto it, 35 meters from the base of the tower, and 65-degree angle with the ground. And we're trying to solve for the length of the wire. Okay, what would you use there? Side length, and now we're asking, is it a right triangle or not? It's, I mean, this tower is going to be perpendicular to the ground, right? So now what would you use? Trig ratio, right? Which one? Cosine, right? 35 is adjacent to 65, so 35 over x would be our ratio. Could you use law of sines? We have, you'd have to go solve for this angle first because it's opposite of 35, but yes, you could. It's just not advised. It's more work than it needs to be. Okay, next one. It says, let's see if I can boil this down. This ranger says that the new ranger station at Bald Mountain would be, the ranger station would be closer to Bald Mountain than the old station is. Whew. Okay. So what are we given? What are we asked to solve for? Closer implies is that angle or length? Length. Okay, what are we given? First question is, well, now it's a length, but first question after that is Right triangle or not? Is it a right triangle? We don't know. So we have to say no. Okay, which option is it from there?
Cosines.
That's a side. That's an angle. That's a side. So which one? Law of cosines, right? Good. And that's the easier case because we're solving for a length. And so it's the kind where you can just square root the whole mess on the right side with your calculator. As long as you plug it in, right? That's kind of the same one. Do I have any more? Yeah, I do. Coming up down here. All right, here's another one. Libby's eyes are 5 feet off the ground, and the angle of elevation, etc., to the Washington Monument, that's actually the Washington Monument, is given there. And it says, how far is she from the monument? So what tool would you use? Trig ratios. Why? That building is perpendicular to the ground, right? Which means it's a right angle. Trig ratios. Which trig ratio if we're trying to solve for x down there at the bottom? What was it? That's tangent, right? Opposite the height of the tower and adjacent what we're solving for. Cool. All right, another one. This says a research submarine dives down directly toward the research lab. How long will it take? How long is a time? So basically we're trying to decide a distance down there. So this distance. Okay. What kind of scenario would you, is that what would you use? Trig ratios. This thing is perpendicular up here at the top. So this is trig ratios. Which one? Opposite over adjacent, so that would be sine. Okay? Is this helping? Like think through that algorithm? All right, this guy's shooting. It says he aims for the center from a distance of 70 meters. So that distance, it's a little bit like foreshortened. If Benito shoots an arrow at this tiny little degree, angle of depression below center, will he still hit? That's probably not the best color. Let's pick something that might work better. Yeah, that's better. Okay, he is 70 meters and he's shooting at some known angle there. Will he still hit the yellow? That's the question. So we need to figure out how much the arrow will drop by the time it hits the target. What would you use? You could. Not the best. What kind of angle is going on right there? Looking directly at your target? What kind of angle are you making with the target? That's 90 right there, right? You're looking perpendicular to your target. So this is what? Trig ratios. Which one? Our x, by the way, would be this length right here. Our angle, you can't see where I wrote it, but it's up there. Which angle, or which trig ratio? Tangent, yep. All right. We did this problem. Do you remember what it was? That was on your last applied homework. Or was it? What did you use, I mean? Trig ratios, you had to do it more than once in that case, right? All right. Hopefully that's given you an idea of where you need to be. Like, here comes a problem. Which one will I use? And it doesn't just have to be these in context ones. Like if I give you just a plain old geometry diagram, it's the same thing. We've got to be good at deciding which strategy to use. Remind me to talk about this one tomorrow. And that one was fine. Okay. The paper for today is short, at least in terms of problems. I think only has 4. 1, 2, 3, 4, yep. Actually, we didn't do that one. I was thinking of a different one, so now I just told you how to do the second one. And let's see. You actually can't do that one with right triangles right away. I'll give you that hint. So I'll have to change that note. Anyway, so your homework and classwork to finish up right now is these 4. You can potentially get them done before you leave. But I do want to point out on number 4, the last one, you should draw a picture. And if anybody's unfamiliar with baseball, let me know and I can help you label where stuff is. Okay? Because that one you do have to be familiar with how a baseball field is laid out. Expect a couple problems on your test like these.
Is it tomorrow or Thursday?
Thursday is your test. So tomorrow we'll do a review.
Yeah, here. The first observed. She said, it's a yes.
Do you guys remember anything about quadrilaterals? How do you find the sum of the interior angles? How do you find, or what are the properties of parallelogram?